This is a continuation of exercise 2.07, question 9. It says this conversion graph shows the linear relationship between the Celsius, which is down here, and Fahrenheit scales for measuring temperature. And the first question is to find a formula for F in terms of C. Now we can see that this is a straight line graph, which means that it will have the formula, general formula, y equals mx plus b, where m is the gradient and b is the y-intercept. So we can see that we've got 2 points here, and the points are 20, 68, so 20 across, 68 up, and 35, 95 there. That's our second point. Now, to work out the gradient, remembering the gradient is rise over run. Just got to be careful here that you can see where the rise and the run are. So we're rising from 68 to 95 because these are the y values. Look, you can also use, there is a formula for gradient, and it is as follows. We know that gradient is rise over run, and always the rise is the y values, so we write it as y2 minus y1, and the run is always x values, and we write it as x2 minus x1. And to do that, if you want to use the formula, your first point is x1, y1, and your second point is x2, y2. So our rise, we know we're rising from 68 to 95, right? But what we do is we subtract the two y values. So we go 95 minus 68, because we're rising from 68 to 95. So to do that rise, you do 95 minus 68. And our run, we know that we're running from 20 to 35. Okay, so from x is 20 to x is 35. But you always do 35 minus 20. Okay, now if you are going to use the formula, you can't get these numbers written the other way round. And 95 minus 68 is 27, and 35 minus 20 is 15. So the gradient is 27 over 15. Now they're both divisible by 3, so if you put that on your calculator, that's the same as 9 over 5, or it's 1.4 actually, if you want to write it as a decimal, but I'll just keep it as a, well, I can write it as a decimal as well. So the gradient is 9 over, sorry, not 9.4, it would be, sorry, not 1.4, it would be 1.8 as a decimal, or 9 over 5. Now, we still have to finish the formula off. We know what the gradient is, so we're going to put that in. So y equals, now I can write it as 9 over 5 if I want, 9 over 5x plus b. Now remembering, so step 1 is to find the gradient, and step 2 is to find b. So to find b, we're going to substitute an xy point into the line, into the equation of the line, and let's just substitute in 20, 68. So we're going to substitute x is 20 and y is 68. Now we can sort of see the y-intercept here. It does appear to be approximately 32, but it may be a decimal, so we're not really sure what it is. But according to this, remember there is a break in the curve here from 0 to 30. We're thinking it should be about 32. Let's see what we get. So y is 68 equals 9 over 5 times 20 plus b. So 68 equals, no, 9 over 5 times 20 is 36 plus b, which means that b is 68 minus 36, which is actually 32. Look, sometimes you can read the y-intercept off the graph. Okay, it does look to be, it does appear to be 32 there. Okay, and we can see that it is 32 when we use y equals mx plus b as well. So our equation is y equals, so now we substitute back that 32 into the b here, so it's 9 over 5x plus 32. Now we know that we do not have a y-axis and an x-axis. We have an f in place of y and a c in place of x. So it will be f equals 9 over 5 times c plus 32. Okay, so that's part A, writing down the formula. Part B, what is the, question B, what is the independent variable? The independent variable is, it's normally what's on the x-axis because the value of y depends on the x. So the independent variable is the temperature in Celsius. So the independent variable is C, which is the temperature in Celsius, or in degrees Celsius. Okay, so it's the temperature in, I'll just put degrees Celsius. Question C, what is the vertical intercept and what does it represent? So this is the vertical intercept here, and it is the Fahrenheit temperature when the Celsius temperature is 0. So we can see here that when x is 0, y is 32. But in our case, the vertical intercept of 32 degrees is the Fahrenheit temperature for or at 0 degrees Celsius. Remember, always the y-intercept is your value of y when x is 0. So always the y-intercept equals the y value when x equals 0. Okay? So it's the Fahrenheit temperature of 32 degrees for 0 degrees Celsius. Okay, now in question D, just use the formula to convert 12 degrees Celsius to Fahrenheit. So we've got y equals 9 over 5c plus 32. So we're going to sub c equals 12, and we get y equals 9 over 5 times 12 plus 32. And we will get, sorry, we don't actually use y, we use f. So f equals 9 over c plus 32.6 degrees. And before I do part 2, which is part 2 says to convert 86 degrees Fahrenheit to Celsius. So I'll be subbing Fahrenheit is 86. Before I do that, part E says to use the graph to convert 12 degrees Celsius to Fahrenheit. So let's do that. So 12 degrees Celsius to Fahrenheit. Now you can see you can't read it off exactly. Okay, so you have to estimate on the graph, which is why we need to use the formula. Okay, so there's your 12, and then we have to come across. Well, it looks to be, if that's 52 and 54, it does look to be somewhere between 53 and 54 degrees. So if you're using the graph, we could say that 12 degrees Celsius equals approximately, I'd say, just under 54 degrees. So maybe between 53 through to 54 degrees, okay, somewhere about 53 to 54, or you could say 53.5 degrees approximately, okay? But you can't really see it very well. Now, for part 2, converting 86 degrees Fahrenheit into Celsius, so 86 equals 9 over 5 times C plus 32. Solving for C, so we would subtract 32. So that's 9 over 5 times C, and 86 minus 32 is 54, equals 9 over 5 times C. Now we would multiply by 5, so not 54 times 5 equals 9C, and then we would divide by 9. So 54 times 5, that's 270. And C would be 270 divided by 9, which is 30 degrees. So using the formula, substituting Fahrenheit 86, we're getting 30 degrees Celsius. Okay. Now let's have a look. So 86 degrees, you can sort of read fairly well off the graph. And coming across, and that's pretty good. You can see that that one is 30 degrees Celsius. Okay, so coming across there and down. So using the graph, we've got that 86 degrees Fahrenheit equals 30 degrees Celsius. Okay, so you'll always get an exact answer with the formula, and you'll get sometimes exactly the correct answer with the graph, but depending on whether you're hitting the line or not. And then part F just says that if the if the temperature in Celsius increases by 5 degrees, what does the Fahrenheit temperature increase by? Now, we can have a look at, I suppose we can use the graph for this if we want, or we could do two different values in the equation. So just remembering, if we do use the graph, it's going to be more than likely an approximation, okay? So it is a bit hard to see a 5 degree increase, but so you'd have to be able to see exactly what a 5 degree increase gives you in Fahrenheit, and it is a little bit difficult. Look, it looks like it's about an 8 degree difference. Okay, but to be like, if you look here, so if you look here, a 5 degree Celsius increase does look to be a bit more than an 8 degree Fahrenheit difference. So I would probably use the formula. Okay, so we did use, for example, we can choose some nice values. For example, if we sub Celsius is 10, and then we're going to sub Celsius is 15, and then we can subtract the two Fahrenheit results. Okay, so when C is 10, we get F is 9 over 5 times 10 plus 32, which, work that out in a sec, and this one, Fahrenheit, is 9 over 5 times 15, sorry, plus 32. And this one is 50, and 9 over 5 times 15 plus 32 is 59. So we can see, therefore, the increase in F, Fahrenheit, is 59 minus 50, which is 9 degrees. So therefore, a 5 degree increase in C equals a 9 degree increase in F. Now that we've worked that out, you actually look at the formula and you can see it actually in the formula. So I really didn't need to do that. Let's look at the formula. F equals 9 over 5C plus 32. Your 9 over 5 is your gradient, which is your rise over your run. So our gradient is rise over run, which is 9 over 5. Now your 9 is your Fahrenheit and your run is your Celsius. So you can see, if you just look at any gradient, for every 9 degree increase you run 5. Okay, so that's how that worked. 9 degree increase, run 5. So we actually didn't even need to do all that. You can actually see it from the formula. So I'll just put this here for part F as well. So you have a 9 degree Fahrenheit increase for every 5 degrees Celsius increase. All right, arrow up means increase. Okay, question 10. Lizzie recorded the value of her computer every 6 months. It looks like the value of the computer is going down. Can we have the time frame there? She graphed this data and drew a line of fit as shown. So she's just drawn a line of best fit through the dots to estimate the values. We have to find the equation of Lily's line of best fit, and we can actually see the y-intercept up here, and that would be the value of the computer originally. Okay, so we've got y equals mx plus b, and we have to pick some points that we can see really well. Interesting, because there are 1, 2, 3, 4, 5 boxes for a 400 increase. So we have an increase of 400. So what is the scale here? So the vertical scale is not going up by hundreds. It's 400. It goes up by 400 for the 5 boxes divided by 5 boxes. So vertical scale is actually 400 divided by 5, which is 80. So each box going up is 80, not 100. So you need to be very careful with that. You always need to check your scale. So this would be 3,000, and this original value looks to be exactly on that second line. So that would be 3,600 plus 80 plus 80. Okay, so we have to find the equation of her line. So I can already see that the y-intercept, so we can actually see the y-intercept this time. And to make sure that you do know that it's the y-intercept, you have to make sure that the x values are 0 at that point, and you can read off the y-intercept. So the y-intercept is 3,600 plus 80 plus 80, which is 3,600 plus 160, which is 3,760. Okay, now the gradient is rise over run. Now, the most accurate way, the bigger the rise and the run, the more accurate it is. So we know what the rise is. If we're rising from here, okay, so if we're doing our rise all the way up there, it's actually 3,760. And we're going to run all the way back here. Now, let's look at the horizontal scale nice and closely. So this goes up by 1, 2, 3, 4, 5, 6. It looks like there are 1, 2, 3, just checking again, 1, 2, 3, 4, 5, 6 boxes going across. So that goes up by 1 month each time. And this last one appears to be at 46 months, so 2 from the end. So the run is 46. Now we have to see whether that's a positive or a negative 46. We're rising up, that's positive, and we're running back 46. So its rise is 3,760 and the run is negative 46. So divide by negative 46. Can be simplified if you put it on your calculator to 1,880 over negative 23, or the gradient is negative 1,880 over 23. So therefore the equation of the line, which is in the format of y equals mx plus b, is, now y is the value of the computer, v, and x is m. So v equals whatever the gradient is, negative 1,880 over 23m, plus, and the y-intercept we said was 3,760. Use your equation to calculate the original value of the computer. Just as I said before, if the x-axis starts from 0, you can just read off the y-intercept. Okay, so the original value of the computer is the y-intercept in this case. So original value of the computer in this case is the y-intercept of your curve, which is 3,760. But if you want to use the formula, v equals negative 1,880 over 23. Now, m would be 0 months. So if you want to use the formula, you would substitute m is 0 into the formula. So times 0 plus 3,760. And you would get 0 plus 3,760, which is 3,760. So that is how you could use the formula to or the equation of the line to find the original value of the computer. Now part C, what does the gradient of the line, what is the gradient of the line and what does it represent? Now the gradient of the line, now we're not going to leave it in fraction form, let's just work out what that gradient is as a decimal, and that's negative approximately, gradient of line is approximately negative $81.74. I'll just, because it's money, I'll just round it to 2 decimal places. So that's what that is, approximately negative 81.74. That's to 2 decimal places. Okay, so I'll just put that to 2 decimal places. That's what the gradient is. Now that means that the value, so therefore the value of the computer, what does it mean? That the value of the computer decreases by $81.74 per month. It's because the units of x are in months, and when we divide these two values, you get negative 81.74, but if you wrote that as a rise over run, it would be negative 81.74 over 1. So the value of the computer decreases by approximately 80 $174 a month. So if you look at, say, 6 months, you're expecting about a $500 decrease, which we are getting, okay? Just making sure that that sort of makes sense, okay? So 6 months, value here is about nearly 300. Here it's a bit over 800. So yeah, that seems about right. Okay, part D, calculate the value of the computer after 20 months and 3.5 years. Just got to be careful here because the formula uses months. So V equals negative 1880 over 23 times M plus 3,760. Part 1, we're substituting in 20 months, so it's negative 1880 over 23 times 20 plus 3,760. We can get our answer there in a minute. And for the second one, it's 3.5 years. So we know that 3.5 years, you have to times that by 12 to work out how many months. That's 42 months. So when you do part 2, you'll have to make sure that you substitute in the number of months, which is 42, to work that out there. So we're getting approximately $2,125.22. Let's just have a look at the graph. So 20 months would be about there. So yes, it is a bit over, just zooming in there. So for 20 months, here it is a bit over $2,000. But again, you can't really read it accurately. And after 42 months, this one, which is 3.5 years, about $327. So what did we say? 42 months. Down here, yes, that looks to be about right, $300 and something. But of course, you can't read it very accurately off the graph. Okay, so formula is really good to give you an accurate result there. Okay, and part E says, when will the value of the computer be 0? Okay, answer in years and months. So it looks like it's 46 months, as we saw before at the beginning of the question. So it'll be 46 months. Now, in years, we know that 36 months is 3 years, so that'll be 3 years plus 10 months, because 3 years is 36 months, that's why. Okay, because 3 times 12 is 36. So that's when the value of the computer will be 0. So value of computer is equal to 0 then. And part F, what are the limitations of the model? So the limitations of the model are that it only goes to 3 years, 10 months. And if we were to try and continue that, you'd end up with negative values, and you don't end up with negative values. So it only goes to 3 years, 10 months, and the value of the computer would be 0. Value of computer would be 0 after this, because the reason is you cannot have negative values. Have a negative value for the computer. Okay,